It's a pleasure to welcome David Berenstein back to Princeton. He tells me that many of the people who were here with him last time, he was here also in the audience. But it's a nice periodicity. He'll be telling us about staggered bosons, Kahler Dirac bosons, and supersymmetry in the lattice. As always, we'll go to dinner. We'll divide it. Please send me an email before 4 so that I can, if you're interested, so that I can make a reservation. If you're not interested, there's no reason to say. Thank you, Mary. Okay, so staggered bosons, if people know what staggered fermions are, they should figure out by the end of the talk that staggered bosons are very similar to staggered fermions. And then there's other versions of fermions on the lattice, like Kahler Dirac fermions. So when I was with Simon Catterall, he asked me, can you do this stuff for Kahler Dirac fermions like you were doing for staggered bosons? And the answer is yes. So we're talking about what Kahler Dirac bosons are, and I'll explain that later. And Kahler Dirac fermions are what shows up when you do supersymmetry. So you marry these two objects together, a Kahler Dirac boson and a Kahler Dirac fermion. You get a very natural notion of supersymmetry on the lattice. So this is something based on a paper I wrote last year before I knew what I was talking about. And then I wrote another paper with one of my students, Thomas Lloyd, in November, where we finally understood what was actually going on in the first paper, especially with regards to symmetry. So it turns out that a lot of the things I thought were new were non-invertible symmetries in disguise. So I will talk about how that shows up in practice, and then I'll tell them a little bit of the story of work that I'm also doing with Simon Catterall right now. Okay, so where did this come from was I was thinking about a very different problem. So I had a conjecture about entanglement entropy in some systems that generalize the Kahler boson. It's this expression as KDB. If you don't know what that is, it doesn't matter. This is where it came from. And then very quickly, what I wanted to compute, I couldn't compute. But what I needed for that computation was to discretize the system in a way that mimicked the original system. And if you take the Kahler boson and you discretize it, the Kahler boson has an anomaly, so something has to break. And then the question is whether you can actually keep the information in a nice way or not. And then I accidentally stumbled on an interesting construction in some way. Okay. So this is to tell you that sometimes these things really are accidental. Okay, so the system that I have in mind is bosonic, and it's very similar in some sense conceptually to how staggered fermions work on the lattice, where you take a fermion and you divide it between nearest neighbors and do something. So this also has a feeling of taking a boson, dividing it between fermions and doing something. And then my lattice friends told me, you should call them staggered bosons. So I did that. And it seemed that there was a new interesting way to make Laplace systems. In hindsight, looking back after all the work we did afterwards, it turned out that it was all non-invertible symmetries in the work, but it was not obvious at the time. And then the similarities to fermions suggest that, you know, one can generalize to a lot of other systems. And this is what I'm going to talk about. Okay. So if you just do generalizations for the sake of doing it into 2 + 1 dimensions, you can get automatically into systems that have fractonic behavior. In this case, it'll be an excess of 0 modes. This is the way we're going to see it in the lattice. And then if you couple it to fermions of the same type, they can do supersymmetry. And I'll show you how to couple these systems to background gauge fields. I don't know how to do supersymmetric gauge fields. Otherwise, I would really be able to do things. But because Kahler Dirac fermions are based on CW complexes of a manifold, you can, in some sense, put all of these supersymmetry on curved manifolds. Okay, all of these constructions are Hamiltonian. So there's a certain sense in which I'm going to talk about the Kahler boson as half a boson. One way to think about it is that it obeys a first order differential equation rather than a second order differential equation. So a Kahler boson is something that moves at the speed of light, and it's one of the square roots of the wave equation that one can have. It only has a left mover, let's say, and if you just take it at face value and you just quantize the left movers, it does not give rise to modular invariant position function. It has a gravitational anomaly. And some people don't like it exactly because of that. But if you think about it as a problem field theory, we know that, for example, the Kahler boson is realized in the quantum Hall effect on edge states. So it's actually a theory of nature in some setups. So the idea is that we're still going to try to analyze the system in real time. And one way to do so is to use a Hamiltonian formulation where I'm going to write some commutator for you. The commutator is because I have Poisson brackets also, and those just curly brackets. And if I have fermions, curly brackets of fermions and Poisson brackets get confusing. So I'll talk about this straight in the commutator language. The commutator of the fields gives you a derivative of the delta function. This is one way to think about the Kahler boson. And then the Hamiltonian is the integral of phi squared over 2. And the derivative of the delta function assures that the commutators are local, and the derivative guarantees that they're antisymmetric. So this provides a Poisson bracket in the sense that you have a constant antisymmetric tensor in the space of fields. And you can use it to compute equations of motion by taking commutators with the Hamiltonian, and the classical equation of motion of phi with this Poisson bracket or with this commutator in Hamiltonian gives you exactly the first order differential equation. And this shouldn't be surprising because really phi that I just introduced here as a table is what people would usually call the current of the current algebra of a C-1 construction. Basically, it's a Kac-Moody algebra, and the Kac-Moody algebra usually has OPEs with a 1 over Z minus Z prime. That would be the way we talk over 1 over Z minus Z prime squared, that double pole. That's the version of a derivative of the delta function in the complex plane. So when you go to the real formulation, the double pole and the complex geometry of the Euclidean formulation becomes this derivative of the delta function. So this part over here is another way to say that you have the Kahler anomaly, and it's a contact term and a total derivative. So this is the usual way of saying that you have an anomalous current symmetry on one dimension. Okay, so the point is that I told you that there is a Hamiltonian that I can write. So I didn't derive the Kahler boson from a Lagrangian. I wrote it straight in Hamiltonian form, and I gave you a quantization of it in the sense of giving you these commutators and a Hamiltonian. Okay, and then the rest of the work is, the system is translation invariant. You decompose in modes and find the raising and lowering operators, and all of that can be done in string. So let's do something on the lattice. So I want to do a half boson on the lattice, and I already told you what I'm getting inspired by. So instead of having a coordinate at each lattice point and its canonical conjugate x and b, I'm going to reduce the variables by half and have only one variable q. And then since q is a boson, it commutes with itself. That's what boson commutation relations tell you. The commutator of q and itself is 0, always finite operator. So if I want to have a non-trivial dynamics in the sense of having a non-trivial commutator, I need to move the commutators somewhere else, and then the non-trivial Poisson bracket or the commutators, you have to move it to the links of the lattice. So what you're going to choose is variables q, and then you're going to put the non-trivial Poisson bracket on the links that connect the different variables. So let me give you an example. You take, let's say, a one-dimensional lattice. You take the q at the kth lattice point, you take the q at the jth lattice point, you write this commutator, and then you pick whether they're nearest neighbors to the right or to the left. If it's to the right, you assign a +1. If it's to the left, you assign a -1. And this is a translation invariant assignment, and then the I is here because I'm using commutators. And there's an H bar hidden in this expression. And I had to pick a sign in the sense that I had to told you there was +1 to the right and -1 to the left. In the end, this sign choice doesn't matter, but I have to pick it, and then I'm going to call this particular sign choice the left mover. From a left mover, I will be able to produce the other sign anyhow. I'll show that in a little bit, but it's important to know that it comes like this. And if you look at this is like a derivative of the delta function in discretized variables, right? You look to the right, you look to the left, and it's kind of divided by the distance between them. So this is like the derivative of the delta function when you're just talking about looking to the right and to the left. Yes.
Is Q like X plus IP? Like how should I think of?
Yes, something like that. I'll show you examples. There's more than one version. I picked only one, but I'll show you exactly how it. But yes, it is like X plus IP between nearest neighbors, or X plus P.
Is Q compact? Q is like the derivative of the compact boson, right?
Q is like the derivative of the compact
Okay,
boson.
so what do you do with the zero mode of the compact boson?
I'll show you in a bit. So all of this will show up at this point. Just trust me that I picked this out of a hat, so to speak. I gave you some commutators, and I haven't been very explicit about the compactness properties of Q or various other things. Eventually, I will do something with that as well. But at this stage, this is just an algebra. And then it's an algebra of operators defined on the lattice. And I just gave you the commutators. And then the rest is, okay, what's the physics of this system?
Is the infinite large lattices?
No. Sometimes yes, sometimes not, depending on.
Oh,
Okay.
but how do you define, if this is a finite lattice, then how do you define the edge commuter?
When there's no one to the right, you declare it to be zero.
Oh, okay.
Right. This is just a statement about the.
On a finite lattice.
We are going to be on a finite lattice, a finite volume, or an infinite lattice. I'm going to do all the cases. Because there's some very interesting properties that depend on if you're on periodic versus an open system, and whether the number of lattice sites is even or odd. Even that matters. So we'll see how that affects the physics. So the idea is that the degrees of freedom are distributed between neighbors on the lattice because that's where the commutators are kind of non-trivial. And this is similar to staggered fermions, where you put different components on the fermions in different places on the lattice. But you cannot say that the right, let's say that you have the left polarization over here and the right polarization on the next one. You cannot say that it's on either one of the two neighbors specifically. It's in both in some sense. Hence, the name staggered bosons. And if you're dealing with fermions in 1 + 1 dimension, staggered fermions are also called Majorana fermions, where you only have a single anti-commuting variable per lattice side rather. So this is in some sense similar to Majorana fermions on the lattice.
Is there a doubling problem here for Poisson?
Of course there is. Yeah, that's what's going to happen in a bit. Again, the Poisson bracket, you're open and you have just a non-trivial antisymmetric constant matrix. Because it's constant and antisymmetric, it defines some notion of phase space, except perhaps for trying to understand what do the zero modes do. But the point is that usually, if you have these, you can basically use it to compute equation of motion and to evolve physics. Okay. The Hamiltonian that I'm going to pick is the one that I'm basically going to borrow what I had from the Kahler boson. The Kahler boson had phi squared, so I'm going to put q squared and sum over all your neighbors. And then if I look at this Hamiltonian and I use my Poisson brackets, the equation of motion for q is first order. And this follows just from the structure of the Poisson bracket. And then you get qi plus 1 minus qi minus 1. And this looks like q dot is equal to twice the derivative. So if you just look at this and you assume that things are long wavelength and things are somewhat uniform, you would say that this has discretized that this is a discretization of the Kahler boson that has accomplished the job. But
Here you don't consider any time derivative because you use arrow.
here, the time derivative comes because of the commutator of the Hamiltonian, and the system is first order because all the Q's are on the same footing.
Oh, I see.
Okay, so I didn't divide things into X and P and integrate out the P's. In some sense. What I really have done is I've basically taken a system, pure equations of motion, and the equation of motion looks like first order wave equation. So things are simple. And then you have to do a mode expansion. So you get a frequency as a function of K. And now we come to the doubling problem. If you have, since the system is first order differential equation, omega is a single valued function of K. So omega is not a square root. This is the point. So omega is, well, in this case, it's minus 2 sine K. This is the computation. And the point is that sine K has some positive values, some negative values. And because the system is first order, the mode with momentum K is conjugate to the mode with momentum minus K. So one of them will be a raising operator and the other one will be a lowering operator. But they are connected by K being a continuous variable. So if at some value omega is positive, next, when it finds itself being negative, there has to be a crossing of zero. And because K, the breathing zone for momentum, is periodic, there has to be two crossings of zero. And the two crossings of zero is the statement that we have a doubling phenomenon. And this is the statement that when you take fermions on the lattice, for example, fermions on the lattice also suffer a doubling problem for a similar reason. Okay? And it's, as I said, straightforward to quantize. Whether something is a raising or lowering operator depends on the sign of omega k for that value of k. And omega of k is equal to minus omega of minus k, and the mode at k is conjugate to the mode of minus k. So this is a statement about the raising and lowering operators in theory. And now we see that there's also zero modes when k is equal to zero or when k is equal to pi. So the statement is that now we got a doubling phenomenon. So if, like we were doing before, things were kind of first order and I picked long wavelength approximations where every Q variable was aligned in the same direction as the nearest neighbor and slowly varying, that's what one would call a ferromagnetic order. And this is what would be left movers, and d omega dk here has a negative value. And then there's a second crossing of zero, and that's a second particle, and then d omega dk is positive for this one. This will be the right movers. And then in this one, when you go from one to the next one, because you're at pi rather than at zero in momentum, you are changing sign drastically. So the important thing is omega of k is a single valued function of k, but what we call the infrared is omega equal to zero, not k equal to zero. It's really important. Infrared modes are the ones with low frequency, not the ones with low momentum. So here there is the doubling. There's two modes at zero frequency. One is a left mover, the other one is a right mover. So we've doubled the system, and this is actually the way it should be, because on the lattice, in the UV, you go beyond the lattice size, there's nothing. So there should be no gravitational anomaly. And we have anomaly matching in the infrared, there should be no gravitation either. So in some sense, the second mode was restored by the statement that you have to match anomalies. Okay, and if you do an ill order, meaning you take your modes a j and you do a -1 to a j, depending on the parity of the lattice side, you can change the sign of all the Poisson brackets because the qj and the next one are going to differ by a minus sign. So you can change the full sign of the Poisson bracket. So the choice between left and right, left moving refers to k equal to zero being obviously kind of easy to access as almost ferromagnetic. And then the right moving Poisson bracket or the right moving commutator will be the one that makes the right mover automatically work out. Great. So now I'm still going to give you the statement that there's symmetry protection, because if I preserve translation invariant, the mode at zero and the mode at pi cannot mix with each other, and if they cannot mix, you cannot, hybridize them and give a mass. So the statement is that even though the system in principle could be gapped, in practice, if you insist on translation symmetry, it cannot. And then the massless bosons are protected even in the presence of, small perturbative interactions where all you would do is renormalize omega of k to some maybe more complicated function. Okay, so it's a critical theory, and now we're getting back to the problem of finite volume. On a large lattice at finite volume, the k is quantized, is 2 pi n over L, and then you want to rescale the energy so that the omegas become quantized over order 1 in the new units. So you rescale things by L, also in the momentum. So what you're supposed to think about it is that you only have one positive frequency mode per n, and negative n is negative frequency, and you put this system together and you get the counting of degrees of freedom like you would have in an ordinary conformal field theory, the central charge equal to 1 of a regular boson. Okay, now this is where it gets interesting. If you go to the infinite line, there's 2 zero modes on the infinite line. One of them is the sum over the Q even, and the other one is the sum of the Q. This is a statement that the 2 crossings of 0 become realized as some particular operators in the algebra. And when you compute the commutators of these objects with everything else, these are actually central elements in the commutator algebra. So we started with a Poisson bracket at infinite volume. There's these 2 objects that commute with everything. So there's 0 modes in the game, and then at finite volume, I have to be very, very careful. Because I was talking about oscillators, but when you have 0 modes, they're not quite oscillators any longer. Okay, so if I do it on a finite periodic lattice and the number of lattice sites is even, then I'm going to draw the modes. So there's the energy of the mode, it's some sign, and then I'm going to take k on an angle, and then k equal to 0, I get 0. And then if I have an even number of modes, I have to distribute these blue dots, let's say, evenly in the circle. And then if there's a 0 mode here, there's another 0 mode here. This is a statement that when I do things in a finite periodic lattice, and I have an even number of sides, I can still distinguish between the even sides and the odd sides, and I have clearly 2 zeros. So if I take periodic boundary conditions, I get the 2 zero modes. If I take anti-periodic boundary conditions, one can check that the Poisson bracket or the commutator matrix is non-degenerate, and therefore there's no 0 mode. Therefore, everything becomes an oscillator. In this case, I already acts by sending k to pi minus k. It's like taking the drawing and doing a reflection about the vertical axis, and it turns a 0 mode of left movers into 0 mode of right movers, and vice versa, if you want to do it. So the one at 0 and the one at pi, they get turned into each other. And this is what's going on. Okay. So if I do it on a lattice with an odd number of sides, let's say I start with a 0 mode here, I have to put an odd number of objects over here. And then you find that if you distribute things uniformly, there's a 0 mode here, you miss it over here. And then if the quantization over here was integers, this one is integers shifted by half. So it's half integers. So in a certain sense, when you do things over here, you get that, let's say, the left movers are periodic and the right movers are anti-periodic. So just by choosing the parity of the number of sides, I can change the boundary conditions from periodic to anti-periodic on one of the 2 systems, either the left movers or the right movers. And then in these systems, parity is broken because you cannot turn the left movers into right movers. Right, if you do a vertical reflection, you get a different sector. The reason why there's only 1 0 mode in this case is because the Poisson bracket is an antisymmetric matrix. And if you have an antisymmetric matrix and the number of entries is odd, there's always 1 0 anyway. So this is something that also happens for Majorana masses. So if you have a Majorana mass matrix, it is an antisymmetric matrix, and then things like that could happen.
Sorry, so what is the phase space in that case? The phase space is odd dimensional.
So there's an even number of variables that have a regular phase space, meaning that it can be turned into oscillators. And then there's a central element. And the central element, at this level, it's not clear what it can be quantized to. So in this story, the quantization of the zero modes, or what precisely I do with the central elements, is still up for grabs because I haven't really told you what I'm doing with it. And a lot of the story will be exactly as to what is the right way to think about that central element. So the phase space itself is, oscillators plus whatever the zero modes are doing. And this is where, in some sense, the conjugate variable to zero modes is missing from them.
In the case with where you had an even number of lattice sites, then the Poisson bracket was regular, it was invertible.
It's invertible for anti-periodic boundary conditions. And for periodic boundary conditions, you actually get two zeros. Yes.
Is there a remnant of this parity thing in Hamiltonian limits?
Yes. That's what's called the non-invertible symmetry. So here I'm telegraphing the future answer, but when I started, this was kind of like this. And if you look at this, and you do it on an open interval, whether you have 1 0 mode or 0 0 modes depend on whether the number of lattice sites is even or odd. If you have an odd number of lattice sites, then there has to be 1 0 mode because you have an antisymmetric matrix of an odd number of entries with a zero eigenvalue. And if you have an even number of zero modes, an even number of sites, then you realize that the Poisson bracket is not degenerate, and then it's like having your straight normal boundary conditions for systems. So there's no zero modes. Now, if you do this counting of zero modes, this is very similar to the counting of zero modes for Majorana fermions. So when Kitae is talking about Majorana fermions on a wire, there's an issue on how many zero modes you get depending on whether the number of lattice sites is overall. It's the same reason. When you need to gap the fermions, you need to pair fermions nearest neighbor somehow, and then you have to do it in pairs. And then the usual pairing mechanism is to write some kind of mass matrix or some antisymmetric mass matrix that lets you give a gap to these nodes. But if the number of modes is odd, there's one that is unpaired, and that is the one that's kind of the one that usually does all the neat topological tricks in these measurement wires. So the idea is that if you look at what the details are, is that the mass matrix that you need to put in is antisymmetric, and at least from the point of view of what matrices you get, they're absolutely identical arguments. So this tells you that these things that are called staggered bosons are working similarly at the level of topology as Majorana fermions, which are also staggered fermions. Okay. So now comes the point of translational symmetry. What is translational symmetry in the system? And then Nati will recognize the discussion we're having there. Is Qj to Qj plus 1 basically getting the variables on one side and moving them right to the next? Is that a symmetry of the system? The problem will be the zero modes. So this symmetry obviously is a symmetry of the Poisson bracket and of the commutators. So if I take this as an operator statement and I just do this replacement, I don't really change the Hamiltonian. So if I'm with periodic boundary conditions, I get the same Hamiltonian on both sides. So it looks like this is an allowed operation. And it is definitely a symmetry of the Q commutator algebra. So it's a symmetry of the algebra that I started with. But when you look at what the symmetry does, it turns the zero mode of even sides into the zero mode of the odd sides. I hadn't told you yet what I've done with them. But as an algebraic statement, because these are central, you cannot turn C odd into C even with an inner automorphism of the algebra itself. That will be conjugation by some element of the algebra. So this object over here is an outer automorphism of the algebra. It's not an allowed operation from the point of view of things that are obvious within the algebra. So it takes the algebra to itself, but the zero modes are doing something. And then the non-zero modes are subject to Stone-von-Neumann theorem. The Stone-von-Neumann theorem tells you that we have raising lowering operators with canonical commutation relations, there's a unique quantization of them. And what that means is that if you go from a system that has that algebra to another one, you can uplift it into a unitary transformation. The Hilbert space of states takes you from one to the other one. So you can upgrade whatever you're doing to the algebra to the representation of the Ising-Loring operator directly. So you can make it into a unitary and make it into a symmetry a la bigger. This one, well, it doesn't quite work if you're in an irreducible representation of the algebra, because these are central, they are numbers, and therefore the odd value that you have here and the even value in principle have nothing to do with each other. So whether it is a symmetry or not really depends on the Hilbert space on which representations of the zero modes one has available. So the statement is that something that is a symmetry of the algebra is not automatically a symmetry of the Hilbert space. This is the important thing one has to keep in mind. And then at the level of zero modes, there's no guarantee that this is a symmetry of the full Hilbert space, even after you take into account all the possible values that C even and C odd can have. If you act twice, so if you do a translation by two, the zero modes go back. Stonewall-Neumann guarantees that you can uplift it to a unitary. So acting twice restores a representation with fixed C, and we can find a candidate target for any state, and we can actually make it into a unitary of the system. Yes.
Is there an operator made out of the Q's that if you conjugate the Q's by it, you shift by one or not?
No,
There's no such operator.
there's no such operator. This is the statement that it's an outer automorphism of the algebra. If it were inner, that would be exactly what an inner automorphism does. But in this case, this is outer. And then this operation of acting twice is like a translation of ordinary conventional theory, where you can basically upgrade it to a unitary acting on the Hilbert space. Now, where does translation by one act by symmetry? On the subsector of representations where the labels of the odd and even modes can in some sense be matched across the lines. So what you have to think is that your Hilbert space is characterized by the values of C odd, C even plus some oscillator. The oscillators go on for the ride, and then everything, whether something is a symmetry or not, gets reduced to comparing the zero mode labels of the zero mode eigenvalues of the representatives. So whether something is a mirror or something else or not depends on details of the theory. And this is where all the magic is. So in practice, what does one do? I want to promote this to a symmetry to the extent that I can. So being very pedestrian, you take the full list of labels C odd, C even. You pick the list of pairs where you can take the C even, C odd to another pairs, to another C even, C odd that is allowed where the labels are swapped. And on those, you can define the symmetry and take the non-zero modes along for the ride. And everywhere else where there's no pair, you just declare defeat and basically extend by zero. So because the C even, C odd are eigenvalues that characterize the representations of the algebra, if I have it not act with some of these representations, I'm okay because the Hilbert space is what it is. And then I basically define this D, which comes from duality, as half translation, because I know that if I do twice translation, I can always make it into a unitary. And I applied where it makes sense. So this translation by half, in some sense, acts only on the subspace of the Hamiltonian that involves this pi projector. And basically what you declare is that D, whatever this is really D composed with pi, which takes away the bad representations. And then this object, when you square it, remember that the pi is around. So when you square it, you do translation by 2. So that's what I would call the ordinary translation. But you have to remember that you projected something out, so you get this projector over here. The fact that there's a projector, and that the projector is a non-trivial projector most of the times, is what makes this into a non-invertible symmetry. Okay. So once you start seeing them, you realize that a lot of the things that I said about the gap of the system and some of these other properties of the system might be related now to the existence of this non-invertible symmetry. And let me show you a little bit how it works. So the point is that I want to understand what this non-invertible symmetry really is. So I want to tell you how to build a half boson from a boson. I have more than one construction. I'm going to just pick one and do the simplest one and tell you how to make elements of a Q that have the correct commutation relations from a conventional construction.
David, I mean, if you have an odd number of lattice sites, then none of this is a problem, right? So then it is a symmetry, a regular symmetry, or?
Yes, I'll tell you what the odd number of sites really means. Because the symmetry will be T-duality, so you have to understand what T-duality is as a symmetry.
But then there's no need for projection in this case.
There's always a need for projection.
Always.
Yes. So let me tell you how to go from a system of n of a lattice of regular bosons. So you have n copies of xp, that's 2n variables. So if I have 2n variables over here, I should go to 2n variables over there. So the idea is that if you start from a regular boson, one way to do it is you double the number of lattice sites. And then you're going to distribute things between the neighbors in some particular way. And then let's say the evens, you pick momentum, and for the odd ones, you pick the difference of the x's. And you can check that the commutation relations, Poisson brackets of these Qs obtained this way are the same commutation relations I got. And the minus sign here is the crucial thing for that. So it's clear that these satisfy the commutation relations, but I started here with a non-degenerate Poisson bracket, and I told you that the other one was degenerate. So I got rid of something. So while it is true that I can start from a regular boson and get one of these other objects, it's not obvious how I got from something that was non-degenerate to something that was degenerate. I threw something away, so what did I throw away? The zero mode for the odd Q is missing because when you add the sum of the x's, you realize that it cancels with periodic boundary conditions. So what you see is that I really went from n variables to n minus 1. That minus 1 took us from an even non-degenerate Poisson bracket to something that has an odd number of variables which has zero mode. And then I told you that in my original construction I had 2 zero modes. So I need to take these 2n minus 1 variables and add one more variable, which is the missing zero mode. The missing zero mode is the one for odd Q. So what does odd Q mean? If I add it as a zero mode, it means I can set it to a constant. And then if I'm in a periodic lattice, the x that I come back to eventually will not be the same x I started with. I come back in x up to a shift. So in a certain sense, one of the zero modes is the center of mass motion. And the other one is a classical version of winding, where when you go around, you come back to the same value shifted by a constant. So the idea is that even though I started from some Poisson bracket that didn't know about winding or momentum, if you look carefully, the 2 zero modes, one of them can be interpreted as winding and the other one as momentum. So it should be no surprise that if the even Q momentum and the odd Q is winding, when you translate by 1 in the system, you turn winding into momentum, and then things get interesting. So translation by 1 acts by sending P to the gradient of X, and by sending the gradient of X to P. It exchanges winding and momentum in CFT. This will be T-duality. So if you're doing the system and you think of taking the large volume limit and turning it into a CFT, the symmetry that's supposed to be this non-invertible symmetry is T-duality, but as I was told many times, T-duality is not a symmetry. Not quite, yes.
So there is also the zero mode of position of X, which is not mapped to anything.
That's right. That's in some sense the conjugate variable to the center of mass P.
Right.
And that one has been sent away in the algebra. So if you have access to it in some other form, then you will be able to restore non-degenerate space. But from the point of view of the algebra that I declared at the beginning, that's nowhere to be seen, and that will be something that you have to supplement.
So some of the Qs and the X and P's are not equivalent.
They're not quite equivalent. They start looking equivalent, but the Qs have a little extra in zero modes, and they're missing a little bit extra in terms of conjugate values. Yes.
So the inverse transformation is also not local. That's also.
Yeah. So as I said, you do T-duality twice or doing the translation by one twice, it's a symmetry, you preserve the central elements, and then this is the translation by one in the original lattice of the XP variables. So translation by two in this staggered Boson variable is what I would usually call translation by one in a regular lattice. So it's correct to call the translation by two in this Boson system, you regular translation, the lattice, and then the translation by half is this T-duality object. And then T-duality is not usually, well, I don't usually teach it as a symmetry, I teach it as an equivalence of two theories. So there has to be some interesting relation between a dual and its T-dual to be able to promote it to a symmetry. It's not automatic.
Has to be at the central radius.
That's how you get the radius. So how do you make T-duality into a symmetry? So first, I will assume that whatever my system is, the zero modes behave like the zero mode or like the labels from some lattice, some regular XP variables. And then I apply the transformation on the maximal set of labels that are mirrored. So that means I take the left moving momentum into the right moving momentum and the right moving momentum into the left moving momentum. And then sometimes I will find the match between the two, and where I do, this is something that takes me some set of, let's say, allowed vertex operators to some other allowed set of vertex operators, or that takes some states to some other allowed states. So it requires, or it acts as a symmetry on a subsector, which is the sets of Q left, Q right, or the K left, K right vertex operators, where I have a match. Yes.
So when you shift by one, it does not matter left and right.
What it maps is the zero mode of the left movers into a zero mode of right movers. If moreover, I do a parity symmetry on the worldsheet, I can be more precise about what's going on. So setting J to minus J. But at this level, what it's doing, it's really taking a field theory and then finding relations with a subsector of the T-dual theory and matching these two where you can.
So if I just think of the full boson left
Yes.
and right, I thought T-duality maps the left moving oscillators to themselves and the right moving oscillators pick a minus sign.
Yes,
Which would be consistent with your dispersion.
absolutely.
But the zero mode is all messed up.
Yes. This is because the C left and the C right are not the zero modes that you would associate these are momentum unwinding. So you exchange momentum unwinding, but that means that when you look at it more carefully, you send K left to itself and K right to minus itself. So it acts by T-duality in the usual sense that it sends the K left. Right. You send C left to C right and C right or C even to C odd and C odd to C even. Sorry, let me. The point is that what we call the left momentum is going to be something like C even plus C odd. And what we call the right moving momentum is going to be something like C even minus C odd. So this one is odd under the exchange of the two, and this one is even under the exchange of the two.
And these are the zero modes, right?
And these are the two zero modes.
And how are they quantize or?
Well, so I told you that I was picking a quantization that comes from a regular boson to have a toy mode for understanding. So I'm going to assume that the C even C odd form a lattice. And at this stage, I would like to have modular invariance, but it's not guaranteed because I haven't provided enough information to give you how that would work. So the point is that there is some set of pairs where I can do this transformation and find the target candidate, and some places where it doesn't. So when I do that, the symmetry algebra is again the same. This d squared equal to translation by 2. And then this is projector onto matching labels. And this is what we call the T-duality symmetry, which has just been extended like I told you. So I promoted T-duality to a symmetry by saying that in some sense there's translation plus some T-duality in the game. And now, as I said,
It's not just a question of the labels, right? It's also
Yes.
the Hamiltonian, you have to give the same energy to the binding modes.
so that happens automatically because this was a symmetry of the Hamiltonian, right? It was the symmetry of the algebra that comes with Hamiltonian, or that preserve the Hamiltonian. So the notion of modular invariance, at least at this level, when you try to take a large volume limit, but still periodic boundary conditions and go to low energies, you have to put it in by hand. Because I really haven't told you in this language what is the origin of the quantizations. And in this setup, I haven't given you enough, and I have some ideas, but the ideas haven't made it to a paper and I'm still confused about some. So if you really want to know, you can ask me afterwards. But we can just consider ourselves to lattice of charges that are compatible with a free scalar, or the question is if there's some other way to restrict and blah, blah, blah. Okay, yes.
When you say C even and C odd takes value in some lattices, so basically you're also adding the conjugate values for them. So you're summing over the values of, let's say, C even being all the integers.
Yes, I'm telling you that they're integers divided by the length of the.
So you're summing over all those representations with fixed value of.
Yeah, again, this is because I borrowed a regular free scalar and tried to dump it into this formulation, including the information about the quantization of C. The whole point is to put this object I found into a more familiar language to understand how things map into each other in this setup. The idea is that if you revisit the notion of gaplessness, the argument I gave were based on single valuedness of the dispersion relation. This is actually a double cover of the regular Brillouin zone. So you should think that the regular Brillouin zone has the positive handpoint, the negative handpoint to each other. And then in the limit of zero quasi-momentum for left movers, they're on one side, and the one for the right movers, you get mapped to this momentum pi, and the translation by one in pi is a minus sign, and this is exactly the minus sign of T-duality. You take the left movers themselves, and you take the right movers and change them. So this -1 difference on the square root is exactly the statement that T-duality acts by -1 choices. Okay. So the idea is that what's really at play is that you insist on the symmetry of the right movers being kind of by -1 versus the left movers, and that's enough to tell you that left times right cannot be put together because that violates that symmetry.
So in the end of the day, what is your Hilbert space? Is it the Fock space of the oscillators of the boson, where any information about the zero mode is gone or not?
No, it's the Fock space of the oscillators of the boson plus something about the zero modes that at this stage I still have to put in by hand. And the way I put it in by hand was to take from a regular boson and just plug that stuff in, including my.
At what radius?
In this one, it doesn't matter, it will matter later. So I will show you examples where the radius is actually very precise. Okay. So now we go back to this statement. Are the Q variables periodic? Are they kind of infinite? Are they finite? If you take the commutators of the Q's and you translate the target space Q by some amount, you still get an algebra with the same commutators as the one you started with. So in principle, you can gauge some of these translations in target space. So either I introduce a gauge field and I go straight to the gauge invariant variables. I'm going to choose to go to gauge invariant variables.
The Hamiltonian was not invariant. The
Hamiltonian
was not invariant.
I'm going to pick a Hamiltonian that is.
Okay.
So the point is that I'm going to start from the algebra of the Q's. The Hamiltonian is whatever I want it to be, but the algebra where I'm acting is not. So I'm going to start there. So I'm going to consider the algebra of gauge invariant variables where I take the Q's and I exponentiate them by some amount. So translations in target space of Q are gauge symmetry. So I'm going to swap the Q algebra for the algebra of the case. So if I do that, because now the Q's are exponentiating K, the commutators of the K produce a phase rather than produce a commutator with a C number on the right-hand side. And then the phase is roughly exponential to the I alpha squared. But there's an important thing about these commutators is that, and now I'm going to put a different hat on my head, is that I'm also trying to do quantum computing. So having finite algebras and finite Hilbert spaces is important. And if you take this omega and make it into a root of unity, then there is a power of k that becomes central. And if it is central, I can replace it by a C number in a representation. And basically, I'll replace it by my favorite number, which is 1. So the idea is that if you start with these objects, and if you take omega at the correct root of unity, then I have something where I have a variable that commutes with everything. And I will declare that these variables for all of them are 1. And what that means is that my algebra now, which used to be polynomials in all the q's, now if I take polynomials in all the k's, because k to the n is 1, then it's a finitely generated algebra over the complex numbers on a finite lattice. And therefore, it's a finite dimensional algebra. If it's finite dimensional, then all its useful representations are finite dimensional, so I can put it on a quantum computer, finitely many qubits. Okay. Again, this was a reason to choose it, but now I'm going to produce a Hamiltonian for you, which, can be also produced from the p and the x's. The k's are basically like exponential of alpha p, and the odd k's are like exponential of the alpha of the gradient x. And the idea is that if I had a quantization for k and I had a quantization for k to the y plus 1, I can kind of push this to a quantization of the x itself. And therefore the x is also periodic, so I can actually try to read off how big my torus is for x. And then when you think about what these objects look like, the k to I, now you're doing finite n-binomial matrices because I replaced my Hilbert space of an x and a p by a Hilbert space of something that involves magnetic translations and that are finite n-binomial matrices that satisfy Hooke's commutation relations, clock shift matrices. So in the even case, I put the q's, and in the odd case, I put p cross p inverse. So I can make a lattice field theory. I think I skipped that. I basically take the simplest Hamiltonian that I can, which is sum of all the k's, but the k's are not self-adjoint. So I take the sum of all the k's plus the complex quantities. And this preserves the symmetry of sending the k to I to the k to I plus 1 that I started originally with. So my T-duality symmetry is preserved. And as I said, I can read off the periodicity of the x's, and therefore the periodicity from the fact that k single valued. And this actually produces now a quantization condition for the zero modes, which is what we will call the radius of the CFT. And then if you just compute it, you just find that the radius is square root of 2n. This is a statement or a calculation that we did. I'll explain where this square root of 2n comes from. The calculation in these x variables is not enlightening. I'll show you the right way to think about it. So
normalization here is actually the self-dual point is root 2 or 1. What is your convention for R?
this is the one where R goes to 2 over R.
So the self-dual is root 1 over root 2.
The self-dual is root 2 or 1 over root 2. Sorry. Square root of 2 over n. It's root 2. It's 2 over R.
So the self-dual is root 2.
Yes, but you cannot do this with 1 by 1 matrices.
But I just wanted to know.
Yes, this is the usual convention of R goes to 2 over R. In the x and p variables that I have here, this is not like an obvious convention. Let me explain why this number is there. In these variables, it doesn't make much sense. You have to trace too much information, but we get a number. And let me tell you what the Hamiltonian is. The Hamiltonian is this k plus k inverse. And here I'm going to tell you what this looks like. So if you look at the literature, these models have been known since forever. The fact that you have these Q's and this P cross P inverse, these are generalization of Ising-like models. These are called clock models because they come from PQ matrices. These are well-known in statistical mechanics. And the important thing is that the coefficient of P cross P inverse and Q is the same. And then when that is true, you're at a self-dual point of some symmetry over here. The symmetry is the one that sends the Q into P cross P inverse into Q. That's known as Kramers-Vanier's duality. So you're at a self-dual point of the Kramers-Vanier's duality. So in the simplest cases, for 2 by 2 matrices, you get actually Ising model in a transverse magnetic field at criticality. For cube roots of unity, you get a 3-state spots model at criticality. So that's the case where omega-3 equal to 1, and this has central charge 4/5. So even though I started with a free boson, with a C equal 1 conformal theory, I end up in theories that have C less than 1. Once you start with 4 roots of unity and further, you end up in spin chains at criticality with central charge equal to 1. The one with 4 roots of unity does not have a U1 current algebra, and the ones with 5th roots of unity and further are a conformal theory with a U1 current algebra. Okay, so you get a non-trivial set of theories where the matrices are very small. That'll be the very quantum regime, and then eventually you get to something that's a little bit more semi-classical in the Q variables. Okay, so what's going on? Translation by one persisted, and we did the same construction of the K variables on all the lattice sides. This was our original non-invertible T-duality symmetry. So what happened? The symmetry in the new variables is what people call Kramer-Vannier duality. So what was T-duality became Kramer-Vannier's duality. And it's also a non-invertible symmetry. And the spin chain landed at the self-dual point for the Kramer-Vannier duality. So in a bit more detail, if you take the Q variables, you can make a big Q variable by taking the product of all the Qs. Remember, these are exponentials of the variables. So to get the zero mode, you need to take an exponential of the zero mode, and this is why you get a product form. And the nth power of Q is equal to 1 because of my conditions that I put on the K operators to the nth power being equal to. Okay, so the symmetry of the zero modes of Q, the original symmetry that I had that was associated to the zero modes, gets replaced now by a ZN symmetry, which is the symmetry of these objects over here. So there's no corresponding symmetry of the P cross P inverse, that one gets canceled out. So when you write this projector, the projector needs to go to the singlet of this ZN symmetry. This is the condition that you can, in principle, find a paired object after you apply the non-invertible symmetry. So because the P cross P inverse telescopes to 0, a periodic lattice, then the only things that have a candidate for landing in Hilbert space are the ones that are ZN invariant. So the statement is that this non-invertible symmetry is also related to the ZN symmetry of the system. And what you get here is that the D squared gives you translation by 1 times the projector on the Q equal 1 sector, which is a ZN projector. And then in the infrared log wavelength, you replace T by 1, and then you use different normalizations from conformal theory. You find some well-known kind of symmetry relation. But the more precise statement is that T-duality 2 over R is going to be equal to the ZN orbifold of the theory. So if you take the orbifold and compare it with the T-dual, you can find that the radius squared is 2n, and then when you take the radius, the square root of that, you find the square root of 2n. This is the statement of the quantization of the zero modes that comes from understanding what the left and the right universe are doing each other and how it is feel. The statement is that the non-invertible symmetry is here playing a role of telling you exactly what the correct quantization of the zero modes should be. Okay. So people did this numerically, they report the same radius numerically with the MRG. We also did exact diagonalization on a ridiculously small lattice. And all of this works, so you actually look at it numerically and you can actually find that just by staring long enough at the list of levels. And the point is that this symmetry that's controlling this stuff is still a symmetry of the finite lattice of finite volume. So all of that is there. The important thing is you're gonna ask which operators survive, and then you find some operators, and then there's some exponentials of x that might survive, and the conformal weight is n quarters n quarters. So if n is bigger than 4, they're irrelevant, and the theory flows to equal 1 theory. And if n is less than or equal to 4, then either there's a marginal turned on that takes you away from a U1 current algebra, or you have added a relevant operator that takes you away from to C less than 1. Okay. So this is what explains this table. And then you work around a little bit more. And then this thing with an extra factor of n is what people call the Tabara-Yamagami categorical symmetry of the groups n, where they also found this square root of n symmetry. So this is that story. Now I'm going to go on to generalizations. So now you have the 1+1 example carefully. And now I'm just going to add dimensions. So I say, what happens if I go to 2+1 dimensions? I forgot to turn this into commutators, but you get the idea. You need to pick a sign choice on what to do with the nearest neighbors. And then if I use the same Hamiltonian as before, I get a non-trivial omega of k, which again, it's a first order set of differential equations. And then I get -2 sine x, -2 sine ky. And the important thing is that there's, this vanishes when some special values of kx and ky come over here. And then there's these two crossings over here, where you get double zeros. This is what shows these things as being fractals with an omega, which looks like a product of two k's. So you get an omega that has a non-trivial dispersion. But the more precise statement is that there's a huge number of zero modes because omega is a single value of function of k. It also satisfies that plus k and minus k are conjugate to each other. And to go from any point to another one, you have to have a crossing of zeros. So if you look at these, you have lines of zeros with values of momenta. And that's the statement that you have a lot of zero modes in some special directions, which is what people call these fractal modes. Okay. And then you can also map them to PQ matrices by the same trick as before. If you do that and you pick a splitting of the lattice sides into even and odd lattice sides, what you do is you take the square lattice, you rotate it 45 degrees and declare it to be the face center lattice. So you paint the corners rather than the center blue. In these corners, you put Q matrices. In this one, you have to have something that produces the correct computational relations. And then you see that this starts to look like a plaquette of Cn, and these things look like some type of field. So what happens is that similar models with finite number of degrees of freedom can be easily obtained. It also has Cramer's Vanier duality where you change the plaquettes for these sites. Okay, so and now this is the stuff where we go to supersymmetry and Kahler Dirac Bosons. So staggered bosons are similar to staggered fermions. How do you do Kahler Dirac? So Kahler Dirac is a very particular type of construction where you assign fermions to triangulations of manifolds or to CW complexes. Put a fermion per phase of various dimensions, and then the usual Kahler Dirac Hamiltonian or the Kahler Dirac action knows about the boundary operator, and you build a system from that. So the idea is to build a commutator bracket for the bosonic variables that follows the information of the exact sequence. What I'm going to do right now is just give you, if you have the boundary operator of some CW complex, you have some integers over here, then I'm going to declare that my commutator of X variables in the various chains takes care of what this integer is, and then it's a commutator, so this tells you that you have the boundary operator, and then because you also have commutators between things of smaller degree and higher degree, the star or the dual of the C is also showing up implicitly. So I just put this information around. I just gave you Poisson brackets or commutators. And now I'm going to give you a supersymmetry, or first of all, a Hamiltonian. I just take the sum of 1/2x.
What was Cn? Can you explain again?
Okay.
J is site in the lattice?
If you take your faces of dimension n, then the C is the boundary operator that takes you from complexes of dimension n to complex dimension n minus 1.
So they're bosons for fights, lengths, phases, and so on.
Yes. So you just put a lot of bosons for these objects. You can still write the similar type of Hamiltonian, and then you just basically declare something like this with Hamilton. The important thing is if you have a Kahler Dirac boson and you have fermions and you're attaching Majorana fermions to the same data that the bosons, then you can easily build some operator which is the sum of x times theta of k. And then you can show that Q squared produces the Kahler Dirac Hamiltonian for the fermion and produces this other Hamiltonian for this. And then
This is supersymmetry, the square of Q is the Hamiltonian.
yes,
But you don't get square of any, the momentum, you don't get momentum.
no, I don't have moment. But
It's not the standard algebra.
it's not the standard algebra. But
Would you say what the Kahler Dirac fermion is?
yeah, so let me go back. Okay. So Kahler Dirac fermions, when you compute Q squared, then you see that there's some commutator of the phi's that show up when the thetas are different. And when the thetas are the same, they square to one and you get phi squared. So you get the bosonic Hamiltonian that I gave you. When you take the Q squared, you get theta times omega, and the omega that shows up here, which is the symplectic form that I built, has the information of the CW complex, so it marries objects of one dimension with objects of a different dimension and the delta operator. The Kahler Dirac fermions are the fermions whose Hamiltonian is constructed exactly in that way, that use the boundary operator and then plot it into the fermions and use the star of that or the star operator to build something that has the right symmetry for Hamilton. And this is the type of fermions that show up when people do n equal 4 supermanifolds on a lattice. So Kahler Dirac is what people claim in these triangulations that produce non-trivial supersymmetry for n equal 4 meals produce. But the advantage here is that I just told you that I gave you this information from a triangulation. I got the Kahler Dirac fermions, and then the zero modes of the Kahler Dirac fermions have to do with homology. So there's going to be appropriate zeros of phi A in the homology that behave exactly like the C numbers, like these objects I had before, the C odd and C even zero modes. So it gives you some type of in principle lattice of things that we can compute. If you have more than one, you can twist by global symmetry. So let's say you have a U1 or you have some more complicated UN symmetry, then you put the same information on the commutators and then you're allowed to twist by your favorite connector between the various lattice sites that will involve some unitary or some group element. In principle, what that means is that these objects are smart enough to be able to be coupled to some background gauge field or some background non-trivial physics. You can also, as I said, it squares the correct Hamiltonian for Kahler Dirac fermions, and then it squares the Hamiltonian I picked up. I'm running out of time. Let me tell you something about the 1 + 1 dimensions, which is a curiosity. I can now take my Hamiltonian and add random numbers. So I can pick them out of a hat with some, random number generator. I can diagonalize my zero modes. And this is what happens. The low frequency zero modes are delocalized. This is the log of the absolute value of the amplitude. And then the ones of the high energy modes, they exponentially decay to the size of some position. So what that means is that the low energy gapless modes are very robust against these deformations. The UV modes can be localized in the sense of Anderson localization, but the near zero modes kind of survive. And this is interesting because you can even check the double. You get 2 exact zero modes because I still have the commutators having a central element. But you see that the spectrum is very doubly degenerate as a frequency as a function. So if you look at these, the statement is that adding some noise doesn't destroy the fact that the theory is gapless, even though you've destroyed, let's say, translation symmetry. So something survives, it's still critical, and there's still this double degeneracy from left and right movers. And then if you have supersymmetry, it also extends to parameters. Another curiosity, well, the reason roughly is that this is like having a non-trivial curved manifold for a circle, where you've picked the triangulation a little bit and said that different segments have different size. But other than that, this is allowing conformity theory and curiosities. When you go to these more higher dimensional symmetries and you ask what is the natural non-invertible symmetry that's around, it's kind of like an insert, like a non-invertible symmetry that turns a complexes of one dimension to complexes of another dimension. The natural one is Poincare duality. So the notion of non-invertible symmetry would act like Poincare duality in these triangulations. In the 1D lattice with an odd number of sides is strange in that it's not a CW complex because You think of some of them as lines and the other ones as
What
points.
is the CW complex?
Is this,
Let's see that thing.
these are two names, but roughly the statement is that
Just think of it as lattice.
lattice with triangulations.
Silence.
And it's the statement that you have faces of triangles or triangulations or more general polygon natures. And you keep track of the boundary of each face, and then the boundary of the face is zero, and then the CW complexes is a way to build a general manifold from triangles.
But most physicists won't go wrong if they just think of it as a lattice.
Right, until you do non-trivial topology or torus or genus one or something like that. This is important because sometimes we do want to couple things together, or we want to study things in non-trivial manner.
Most of us would be able to imagine a lattice and a general topology.
Yes. In any case, the statement is that there's a recipe that lets you build it. But in the 1D lattice with the odd number of sides, you can think of the even sides as the links and the odd sides as the points. So, or as the vertices. So when you have an odd number of sides on this half boson, it means that you're changing the even to the odd. So this is something that's kind of non-trivial from the point of view of whatever you're doing in these triangulations. It's not a standard one. This is the one where you're also doing T-duality non-trivially in that the left movers and the right movers have a non-trivial periodicity. So if you actually look at the literature of what people call the object where the left movers are periodic and the right movers are anti-periodic, this is what we call twisting by T-duality. So you've applied T-duality and you put a -1 sign on one of the sectors. This is what people call the non-trivial duality defect in states, where you have a non-trivial boundary condition that realizes the duality as you cross the border. So here the statement is that depending on whether you have an even versus an odd number of sides in my theory, you have either regular boundary conditions or you have one of these duality defect boundary conditions. So how these duality boundary conditions show up depends on the parity of the number of sides in the UV theory. And this is kind of the non-trivial mixing between notions of the UV and notions in the infrared. Okay, I think this is it. Hopefully, yes. So I gave you a normal construction of lattice algebras, meaning I was able to engineer some interesting stuff out of commutators where how the lattice is connected plays an important role in defining the algebra. They have non-trivial commutators between neighbors. They automatically realize non-invertible symmetries and immediately lead to interesting models that include critical spin chains and fractons and similar systems to discrete. Staggered bosons are very similar to staggered fermions, and put together you can get very easy supersymmetry on the lattice, including on non-trivial curved manifolds. And then that's it. I think, yes, that's it. Okay.
Thank you, David. Urgent questions, yeah.
Oh, sorry, no, I can just wait.
No, that's okay.
Oh, okay, I was gonna ask about the Anderson localization slide, since you
Yes.
said that the Anderson localization happens for high energy states.
Yes.
And then you said that the zero modes are protected. Is it just the zero modes that are protected, or is it also like low energy states?
All the low energy states are protected and their wave functions are non-localized. And it's just the UV modes that are sensitive to the extremes of this distribution of couplings, where suddenly you have an over excess of energy in one place and you cannot kind of distribute it to the sides, so it ends up being localized. But I don't understand why it's so robust for the low energy modes, except that, you know, even when you break symmetry, you still remember something. Yes.
Is this related to the fact that, so in the Hilbert space that you said C even is integers and C odd is integer.
Yes.
You could think of C even and C odd as two symmetry charges that generate
Yes.
two U1s. And are these basically the U1 momentum and U1 winding, which have a mixed anomaly? And your changing of the coefficient doesn't break this U1 times U1 symmetry. That could protect this gapless.
Well, it does because it's not translation invariant. So I've kind of, in some sense, maximally changed what happens on one side next to the next.
Yes, but I'm saying it could be protected not by the translation symmetry, but by this U1 momentum times U1 winding, which have a.
Well, yes, the two zero modes survive, and then hopefully that's enough to keep the other ones nearby close. But it's not guaranteed, and that was the point. Again, I wrote that in some sense before understanding that the non-invertible symmetries were playing a role, so.
Lots of questions, so
Yes.
maybe we should thank David again, but before we do that, I want to remind you about dinner. Please send me an email before 4 p.m. if you're interested, so that I can make a reservation. Thank you.